beneath God's light she flourishes.
Thank you for that. Now I'm going to do a little bit of a shameless pitch for Caltech. This is the Caltech logo. And I think the Caltech logo actually means something.
Yeah, he came. That's nice.
Can anyone tell me what this means?
Go back one slide.
What does this mean? So this, it signifies, first of all, it's a torch, right? So, research universities are torch bearers, right? So we go where there's darkness and we shed light. And so it signifies innovation, discovery, that kind of thing. But if you look closely, there's two hands. What does that mean? The passing of the torch. So universities, you know what you do? You pass on something to the next generation. Knowledge, discovery, whatever it is, your legacy. And so as I was looking at this, I was wondering, as a professor, what am I passing on? I realized, I was a student here at Stanford 15, 20 years ago when I attended many ISL seminars. And the truth is, I don't remember most of them. And I'm pretty sure 15, 20 years from now, you won't remember the content of my talk. And so my passing of the torch will be that you'll hopefully remember there was a crazy professor the week before Halloween presented as this. So that is my passing of the torch. Not to the top. This is hot and uncomfortable. I think I've had enough of this gorilla pose. So that means with your permission. From my kids, and I asked Tara to take pictures, so I have evidence that I actually did this.
You also have it recorded here.
It's recorded too? Okay, so enough with the shenanigans. Let's go to the top. Okay, so we'll start off saying a few things about information theory and coding and control at a very high level, and I'm sure this is stuff you all know. Then I want to talk about an area where we can have an interplay between these two areas that have more or less, I would say, developed independently, and that's in issues related to coding for interactive communications. And I'll talk about this in a concept called tree codes, and doing control over noisy channels. There's something called anytime capacity comes up. And so most of this talk will be kind of review of the literature and some ideas, and then the latter part, basically I'll describe what the contribution of the talk is. And it turns out that the key idea is embarrassingly simple, but it's surprisingly effective. And so that's actually a good thing, because most of what I do is complicated and ineffective. This actually works. And so at the end I want to conclude, and then again I want to really address the main question of the talk, which is what can coding do for control. And if you read the abstract, I kind of hid it away at the end. Okay, so we all know about single user information theory going back to Shannon. You have your channel, which is described by conditional probability, because your channel acts randomly on stuff. If you transmit X, you don't know Y, you just know the distribution from which Y will be delivered to. And so the beauty of Shannon's work really was that he showed over unreliable channels of this sort, you can actually communicate up to a rate, which you can explicitly compute. It's the channel capacity. We all know this. Now the key idea here is block coding. Again, you know all this, and I'll just repeat it. And the intuition, again, looking at it from miles above, is that with a channel like this, the behavior of a channel over a single use is not really predictable. If you have a binary symmetric channel and you transmit a 0, you don't really know whether you get a 0 or 1. But the behavior over for many channel uses is. Okay? If my channel introduces errors, say with probability P, if I use this channel many, many times, I can say that I'm going to see NP errors. So if I have a code that can protect against NP errors, I can get things through kind of error-free. Okay? And so the idea is having this block coding idea, having these long blocks. And so as a result, one could say that information theory or information theorists or whatever, they live in asymptopia, in this regime where block lengths can grow. And that's not necessarily a bad thing, right? I mean, asymptopia can be something out there, and we can strive to achieve it, just like we strive to achieve utopia. But the important thing, again, is that, you have block lengths that grow. And prior to Shannon, I guess people had the notion of, binary signalings and sending zeros and ones and all that. But in the absence of the notion of block coding, what they were confronted with is if you wanted to transmit a single zero, you can't really protect it while maintaining a rate. I mean, the best thing to do if you want to transmit a single bit maybe is to repeat it many times. But if you want to get any kind of error that's very low, you have to really sacrifice a lot on the rate. You may have to transmit 10 zeros, 20 zeros. And so you lose by a 10 for a 20th the rate. With block code, on the other hand, because you're able to transmit many bits at once, you don't have to take that kind of rate hits. And that's what capacity gives you. And so there's a big difference between trying to transmit short messages reliably and long messages. Long messages can be reliably sent. With short messages, that's not necessarily the case. Okay, and so we all know about how you do this. So you have a string of bits, and you encode them to a longer string of bits. You do some kind of encoding, and if you, I won't go through the math here, you know all of this. And so up to capacity, if you do things right, you can get probability of error that gets very close to zero. Okay, and so it's a nice theory and an elegant result. There's two caveats. On the face of it, we're not limiting the computational resources of the transmitter or receiver. We don't know how much that will take. And again, it assumes very long delays, which in some applications are perfectly okay. In practice, of course, people know that you have to deal with finite block lengths, and so people worry about that kind of thing. I know Sergio recently has very interesting work looking at the trade-off between probability of error rate and the length of the code and so on. And in practice, people, there's been 60 years of coding theory trying to get to Shannon's limits, and coding theory is something that constantly surprises you. There's always new innovations, and the most recent one is Colloquium. And so this last sentence, it's fair to say that in many cases we now know how to approach Shannon's limits. Okay? But you can have a critique of this too, right? You can say, information as Shannon described it, if you look at the way we measure it, really only deals with the probability of the occurrence of an event. It's the log of 1 over p. It doesn't depend on when this knowledge is revealed to us or what we want to do with it. And part of the strength of information theory really is that it's stripped away this context. Right? When you want to develop a theory, sometimes it's important to know what to strip away and what to keep. And so we get a lot of the beautiful theory because we strip away this. But in some situations it might matter, coming here, say, from Pasadena, if it's going to rain, say, at 5 o'clock here, if you tell me it's going to rain now, that's not very useful information for me because there's not much I can do. But if I knew it before coming here, I'd bring an umbrella and whatever. So that information is more valuable to me, even though the likelihood of it raining here at 5 o'clock is whatever it is. Okay, and so it's not really clear how to bring in the notion of time into information theory. There are some attempts, but I would argue that they're not adequate. And again, it's not clear that we can have a nice theory here because it may very much depend on what it is we want to do, what cost functions we care about. So there may be no elegant theory even to look for. So that's all I want to say about this. Let me say a few words about control. So control, at the highest abstract level, you have a plant and you have a controller. The controller observes the output of the plant and wants to influence its behavior through a control input. So it does to regulate it in some desired way. Okay? Now the key constraint in control is that the controller has to act in real time. It has to take a control action as soon as it sees an input. It can't wait, as in a communication system, for all the inputs to come, because by then the system might have done something undesirable. And so a very rich theory has developed for control, and kind of independently of information theory, primarily because maybe, information theoretic notions of the time were not needed, because controllers and plants in the old days were co-located. There really wasn't, much, disturbance, or there weren't, too much issues with these two links here. You could just draw them as lines and you were fine. Okay, but increasingly, we have applications where this is not the case, where the plant and the controller are not co-located. You might have some remote plant, controller somewhere else. The output of the plant is, say, observed, quantized, put into packets, sent across some network, and the network could be lossy. Packets could come with, delay. They could be dropped, whatever. And so the question is, how do you deal with this? And the point is that the conventional, coding theoretic approach won't work. If you attempt to make these channels lossless, which is what coding does in communication, it takes a lossy channel. Block coding essentially makes it lossless. Won't work here because you may not be able to tolerate the delays. Because the encoder here cannot transmit until it's observed lots of inputs, and the decoder cannot begin to decode until it's observed lots of inputs. That delay. And it turns out that if you do know coding, so you could also say, okay, let me forget about coding, let me just look at the output here, and do the optimal controller based on what I observe. It turns out that in many cases that won't work either. These results of Sinofolia et al. That demonstrate this. So let me give you an example. And so to simplify things, I'm assuming the controller to the plant is a perfect channel. We only have a lossy channel here, and I'll assume that this lossy channel is an erasure channel that has an erasure probability. So in this simple setting, I'll assume that these measurements are quantized precisely enough into packets. They go across this, so they're either perfectly received or not received at all with probability epsilon. And this is the plant we're trying to control, and it's unstable because it has an unstable pole 2. That's the setting. And you can do the optimal controller here. Given this information pattern that sometimes packets are dropped, finding the optimal control, the best thing to do is not difficult. It's actually simple control. And so this is the performance. I'm looking at the mean square error of the state as a function of time. So 1 to 11, I guess. And for different probabilities of packet loss. And so when there's no packet loss, this is the performance. It goes to an asymptote, I guess, around 3. When there's 10% packet loss, it goes to 4.5. 20% packet loss, a little over 10. And by the time you're hitting 30% packet loss, the system's unstable.
What's the optimal controller trigger?
So here this is an LQG control. So I'm minimizing an LQG cost. And I'm only showing you part of the cost. There's also a control cost. So in this case, separation holds. You do a state feedback control law based on an estimate of the state, and the estimate of the state is the optimal. So when you get a measurement, you do a time and measurement update on the Kalman filter. When you don't get a measurement, you just do the time. That's optimal. Okay, so that's the issue. So
sorry, you're saying that for the first 3 curves, they tend to...
Yeah, they will go to an asymptote. And the third one. In fact, in this scalar case, you can actually compute where this phase transition occurs. In general, if it's a more complicated model, we don't know how to do that. But there's somewhere between 20 and 30% where instability occurs. And in this special case, you can compute. I just haven't done that. It's in Sinofolia's original. Okay, let me show you another example. So this is distributed consensus. So it's not a control problem, but it'll be related. So I have here 3 agents, and they're connected in this particular way, and each has some initial value x01, x02, x03, and the goal is I want to compute the mean of these 3, and I want to do it distributedly. So at the end, I want these guys to reach consensus on the average of their values, which is 1/3 of the sum. And so an algorithm that can do this is the following. Each node looks at the difference between its value and its neighbors and adjusts its current value according to that with some positive parameter alpha. guy has one neighbor, so it looks at the difference between that neighbor and itself and updates that way. This guy has two neighbors, so subtracts two things and updates, and this guy has one neighbor. Okay? And so you can look at, and there's a linear equation essentially relating the values at time t to time t plus 1, and that's given by this matrix W here. And the only thing to note about this matrix W is that it's doubly stochastic. The rows and columns add to 1. And as a result, if you raise this to some power and let the power grow, which is what happens if you continuously do this protocol, it'll converge to a rank 1 matrix, 1 on the left, 1 transpose, the all 1 vector on the left, and the all 1 vector transpose on the right, which means that in the limit, the 1 transpose multiplying your initial x's means that you're taking the average. The 1 on the left is saying that you're getting to consensus. Okay, so this is fun. Now what happens if we have erasures? Okay, suppose let's do this same thing over erasure links. So at some time, if I have an erasure here, this guy suddenly has, is not receiving anything from 2, so essentially it's not seeing a neighbor, and so does no update. And so what happens to this matrix is all of a sudden it's no longer doubly stochastic. And once it's no longer doubly stochastic, its product won't necessarily be doubly stochastic either. This is the transition. And so what do you think happens here? Do we get to consensus? Or, do we get consensus to the mean? What do you think? Yes. So it turns out in this model you will get to consensus, but not necessarily to the mean. You will get to consensus to some random value, and that random value depends on the realization of the erasures. So here's an experiment. This is a network. Rather than 3 nodes, I have 20 nodes. The topology doesn't matter, but it's a line topology here. There's 30% erasures. And so this is really 20 different curves here, one curve for the value of each node. And as you see, they achieve consensus at some value, but the true mean is this thing in red. So you've actually reached consensus, but to something that's not the mean. So that's something certainly that you don't want. Okay? So the question is what to do. So we saw 2 examples where having these erasures has an effect. One was the control problem. And again, in the control problem, we have to make decisions on the fly, which is why we couldn't do conventional decoding. In the consensus problem, it's the same thing. You're sending these short messages between users. And there's a lot of feedback involved, because what I send to you gets averaged with something else, it's sent back to me, and so there's a lot going on. And so the question is, how can we solve these problems? Is there a way that I can stabilize this plant? Is there a way that I can actually make sure that the protocol I'm interested in, consensus in this case, works over erasure? So it turns out that the theory to deal with this is related to the problem of coding for interactive communication. Okay? So this is a 2-party communication scheme. In Shannon's usual setting, you have a transmitter, you have a receiver, and the transmitter has a long message that it wants to get across to the receiver. Here, Alice and Bob, they each have some private messages, X and Y, but they're not necessarily interested in sending X to Bob and Y to Alice. They're interested in some conversation, some protocol. Okay, so X, for example, could be a binary representation of an integer, Y a binary representation of another integer, and these guys say want to compute the GCD of these 2 numbers. Think of something like that. And the way it works, that they're doing a conversation, so they're sending short messages to each other. So Alice sends something to Bob that's a function of its private message, and then Bob, based on what it observed and what it has, sends something to Alice, and then back and forth. Alice sends something based on what it has, what it sent earlier, and what it observed. And this is a protocol. So at the end, maybe they compute the GC. And so the question is, can we do this in the presence of noisy links? Okay. So I'm sending these short messages across, but not every now and then they could be corrupted. Can I guarantee at the end of the day that we will have computed the GCD? Okay. So this takes me to Leonard Schulman's 1993 PhD thesis at MIT, where to look at this problem, he introduced, there's some debate as to whether it's a new paradigm, but in this context it certainly is. It's something called a tree code that solves these problems. problems. Now, I won't go into the details of how you can solve this with a tree code, what the protocol is. Let me just describe what the tree code is, and we'll see how it emerges in the control context. So, again, I apologize for my picture, but a tree code is basically, it's a semi-infinite d-array tree. So it's a semi-infinite tree. In this case, it's a 4-array tree because there's 4 branches emanating from each node. Now, what these tree codes do is essentially they map an input bit sequence, semi-infinite, to an output bit sequence. And so in this case, every time you're inputted 2 bits, or if you will, an alphabet size of, general of D, that determines, if I start at the top, which of these branches I'm going to traverse. So, if the alphabet size was 4, then I have 1, 2, 3, 4. If the first symbol that comes is 2, I'm going along this branch. So it determines how I go down this tree. And then the way I map to the output is that I assign to each branch on this tree an element from the output alphabet, which is a larger size D prime. So for example, here, if I wanted to rate half code, I'd have an alphabet of size 16, so 4 bits. 2 bits would determine which branch I take, and then each of these would be labeled with 4 bits, and those are the 4 bits that I would transfer. So it's a tree. And so the next time I get an input, it determines if I went down this. If the next one is a 3, I go down here. The next one is a 4, I go down here, and so on. And each time I just read off the label from the larger alphabet size as to what I should transfer. Is this clear? I mean, this is the one conceptual thing in this talk. I hope it's clear. So this is really a mapping from an input sequence of a smaller alphabet size to an output sequence of a larger alphabet size, and the rate is just the ratio of the log of the 2 alphabets. Okay? And the important thing is that this represents a causal code. That's the critical thing. Because the reason why I'm saying it's causal, if you look at a block code, let's say mapping input bits to output bits, if I have 2 input bits that are common up to some point, the output bits have nothing to do with each other. Whereas with a causal code, they have to be identical. And that would be the case, because if I have 2 inputs that are identical up to a point, up to that point, they'll traverse the same path, and so they will output the same. So it's just a representation of a causal code. So that's a structure, but for tree codes, what Schulman required is something a little bit more, and so this is the key. Okay, so for every pair of paths, so you look at the semi-infinite tree, you take any 2 paths that have a common ancestor, and then you go down by some length, say n, for any value of n. What you require is that if you look at the output code words for these 2 different paths, they should have a Hamming distance that's at least proportional, or to a fixed proportion of n. Okay, so it has this, and Hamming distance here I mean loosely. This is a higher alphabet size, how many times they don't agree on that. Okay, so that's what we require. So it's a structure where you're labeling the trees in such a way that for any branches with a common ancestor, this distance properly holds. Okay? So this is a definition, and so Schulman's main contribution was to show that such things exist. So you can actually come up with a labeling of this tree so that this distance properly holds. And furthermore, and this is what I don't have time to go into, he showed that if you do ML decoding on this type of thing, you can allow for reliable interactive communication over noisy links. That's the thing. So this is the type of code you need, and if you do ML decoding, that's what you can do. Now, so this is a very elegant theory, and it's now, 20 years old. Oh, no, not 20. Almost 20 years old. But there hasn't been, a whole lot of work coming from it, and the problem is because, it's nice theory, but there have been no explicit constructions for tree codes. Schulman just proved that they exist, and his proof for existence is not a high probability proof. In traditional coding theory, the random coding arguments that people use essentially show you that good codes exist with high probability. Schulman just proved existence. There was no high probability. And there's no tractable decoding. We don't know how to decode these efficiently. And as I said, existence does not hold with high probability. And so as I said, there's been scant progress in this area as well. Nonetheless, at the time our work came out, there have been some very recent results, and so I'll mention 2. There's something called potent tree codes, developed by Gellis and Sahai. This Sahai is the older brother of the Sahai that I'm going to talk about in a moment. He's at UCLA, the younger one's at Berkeley, he's at relaxed these requirements a little bit and can prove existence of high probability, but his codes are not strong enough for the control problem I want to talk about. And there's been some improvements to Schulman's protocol in terms of how you map these tree codes to protocols, and that's recent work of Braverman from Princeton and Rao at the University of Washington. Okay, let me now move to Sahai's PhD thesis, where he looked at a very specific control problem. So here's a unstable plant, and I want to stabilize it over a noisy channel. And the way I'm going to do it is I'm going to look at the output of the plant, I'm going to quantize it to some bits, and then I'm going to causally encode it with something like a tree code. So what that means is every time I see bits coming from the plant, every time I see a bit, if it's a rate 1/2 code, I'm going to generate 2 bits. And the 2 bits are going to depend on all the bits I've observed so far. It cannot depend on the future bits. And then we send this across the channel, and then I have a decoder that causally decodes. So at every time, once it observes an output, it'll try to decode the entire input bit sequence using what it has currently and not look at the future. And then we go to the controller. The question is, can we design the encoder-decoder to make things work? And let me do a toy example to show you what the requirement for stability would be. It's a toy example, but it shows you the essence of the problem. Okay? So here's an unstable system. So it's a scalar system. X is the state. It's unstable because A has magnitude bigger than 1. And then for simplicity, I'll assume that the input is just +1 - 1. So you can either go left or right. And so you can think of this as being a random walk, but an amplified random walk. So it's unstable. Okay? And let me assume what I want to do is to track the state. Let me not even think about control. Because if I can track the state, then I can control it. So let me worry about that. And so it's easy to see if I want to track the state, if I know, whether at each time Wi was +1 or -1, I can just plug into this equation. I'll know what the state is. So, and that's just one bit of information. So at every time if I just have this one bit of information telling me whether we step left or right, that should be good enough. Okay? And so what we're going to do in this simple setting is I'm going to use an encoder that takes this bit sequence representing whether W was 1 or ±1, and I'm going to causally encode it and send it across the channel. And the decoder at each time instant I will attempt to decode the entire history. Okay? So it decodes the current bit, the previous one, everything, and I'll call those things B hat of J given I. Okay? I is greater than or equal to J. So that's what we want to do. Is this clear? And so there's one definition I need to have, which is this probability of error of I and D. So this is the probability that I'm decoding at time I. So I'm saying at time I, I'm decoding the entire history of the bits. And the first place I make an error is D steps back. So this is the probability that everything is correctly decoded, provided J is less than I minus D. So everything before D, I'm assuming that has been correctly decoded. My first error is made D steps back. That's what this means. Okay? So with this definition, it turns out you can look at, say, the mean square error of tracking the plant. And you can kind of expand it in terms of this event, right? So if I make an error D steps back, the most error that happens after that is essentially like A to the 2D, because it's squared. And so you get this expression here. So A to the 2D multiplies these probabilities, and so it's now clear. If I want to be able to track this plant, this probability has to decay stronger than A to the 2D. So that's the requirement. So at any time that I sit and decode, I'm decoding all the bits. I want these bits to get more and more reliable, the probability of error to decay as a function of delay, and I want it to decay exponentially and faster than the unstable mode of the plant. Okay? And this is, this is essentially where tree codes happen. The minimum distance requirement that Schulman had in his tree codes is what will guarantee this when we do ML decoding. Okay, so I can now introduce essentially Sahai's main result. So he defines something called anytime capacity. Again, I don't know how critical it is. Anyway, it's something that depends on some parameter. It's a capacity that depends on a parameter lambda, And basically it means that the channel will have this capacity if for all rates less than this quantity, again depending on lambda, there exists a causal encoding and decoding scheme that guarantees a probability of error that decays swifter than that. Okay, that's the definition. Okay, so if I have a encoding and decoding pair at rate r that guarantees this for every I and every d, I say, r is less than the n. And the theorem basically is if you have this unstable plant, what you do, you take the output, you quantize it to k bits, k has to be bigger than log of lambda, and the rate at which you transmit, so you take these k bits and you turn them into n bits, has to be less than the n. And the proof is based on tree codes. It uses tree codes. So if a tree code exists with these properties, we throw it in, we're done. Okay, and again, the idea basically is just this, that you can bound. And one thing I should say is that here, I was looking at squared error, so 2D came up. If I wanted absolute stability, D would show up. So depending on what moment you want, this becomes more stringent. And an interesting thing is that